Hi. So, in the second lecture of this module, we started talking about the curve fitting problem, or more explicitly, the polynomial curve fitting problem, where we say that we were given a bunch of data and we wanted to make certain predictions on that data. So, we started looking at a high level on how to create models that we can use to make our predictions. So this was a simple case of linear regression, and today we are going to be revisiting this problem again and start hinting towards how we can apply a Bayesian treatment to this problem and what kind of advantages would we gain from applying such a treatment, essentially. So let's actually look back at what that goal was when we're talking about curve fitting. So the first thing is we're given an input variable, right? So which is our data set. So first we have the x component. So we have x here, which is, so we can assume that this is, I'm just gonna make this like a vector type thing. I'm just using this notation for convenience. So we have this x1 up to xn. So you can think of this as scalar variables. So this is our input data. So this is kind of like a refresher for what we went through in the second lecture. So this is our x variable and this is our target variable. So I'm just gonna again indicate it like this just to show that it's a vector. So this was from T1 up to Tn transpose, right? So this is a vector and this is a scalar, the one that we see here. Okay, so we are given this data set, right? This could perhaps, x could perhaps represent the different sizes of a house, for instance, and the target could be the corresponding prices of those houses, right? So what we would do is try to learn a model that, like, given the size of a house, we try to predict the price of the house. So that's kind of like an example of what kind of problems we could solve using linear regression, right? But one thing we didn't actually, we actually hinted at it, but we didn't actually talk about what we meant by it, is that we can actually express the uncertainty of our target variable using a probability distribution, right? So given that we have some model, so let me just plot this out to make it clearer. For instance, this is, so let's say these are our data points or whatever, and we want to devise some kind of model, and then our model looks something like this, right? And what we had said is, if someone, this is our t, for instance, and this is our x. So if someone wanted to know the value of, say, x0 here, they would come to this part of the curve. Let me use a different color for this. So they would come to this part of the curve, and then they would get the corresponding value of t0. This is what we had said, right? But the thing is that t0 is not a perfect value, right? There is some uncertainty here, right? So when we look at, this t0, there is some uncertainty. Because this is not a perfect model, it's the best model we could actually implement given the data set, but we want a way that we can actually express this uncertainty, right? That's one thing we can think of. So one way to do that is using probability. This is actually the whole point why we went through multiple lectures talking about probability. So what we can say now is that the probability of t, right? So here I'm just writing this more generally. Given x, comma, w, comma, beta, right? So if you remember, actually I'll talk about this in a second. So we can say this follows a normal distribution, right? We just giving this as one example, a normal distribution, right, of t given, so normal distribution over t where the mean is yx comma w and the variance is beta inverse. So if you remember, we had said that beta was actually 1 over sigma squared, and beta was actually representing the precision, which will make more sense when we go into future lectures. But for now, you can just take it as like, instead of having sigma squared, we just have the inverse of beta here. So this notation will make things much more easier when we look at the other distributions or the Gaussian distribution in more detail in future lectures. Okay, so this is how we express our probability distribution over t. So probability of t, our target variables, given x, our data, w, the weight vector, and beta. And we say that this follows a normal distribution, right, over t, which is our target, which is parameterized by our mean, which we represent by yx comma w, and beta, the inverse of beta, which is our precision. So this is the thing. We're trying to use our training data, x and t, to determine the values of our unknown parameters, w and beta, right? And we said, how do we do this? Well, one thing we can do from the previous lectures is actually just take the maximum likelihood estimate, right? Because if we take the maximum likelihood estimate, then that should give us a value of w, that should give us a value of beta. And we already saw how we can actually take maximum likelihood by of the Gaussian in the previous lectures. So if you don't remember that, you can just look back. So that's what we have. So we can better express this, of course, by saying now the probability of t given x comma w comma beta, right, is equals to, so this is the product, right, between n is equals to 1 up to n of the normal distribution of Tn. So now we're just assuming that our data set is independent and identically distributed, what we had talked about before, the IID assumption. So if we have an IID assumption, then we can just multiply the probabilities here. So given y xn comma w and beta minus 1. So here we are assuming independence, right? So that's like, if we assume independence, then obviously we can multiply out those probabilities. That's the idea behind this, or the idea behind multiplying all this normal distribution variables and stuff. So what we talked about as well was, well, if we want to do maximum likelihood estimation, it is much easier for us to perform the maximum log likelihood rather, because it makes things easier to solve or to optimize. So we had represented the ln the log of p t given x comma w comma beta. So this is more like just revision on the things that we already covered, maybe with a slightly different notation because now we're using beta and not sigma squared. So we have minus beta over 2, right, summation from n is equals to 1 up to n of yxn comma w minus tn squared plus n over 2 ln beta minus n over 2 ln 2 pi. So this is how we said we would express the logarithm of this, right? So if we actually perform the maximum likelihood estimate with respect to w, right, given this equation that we have here. So if we take the derivative with respect to w, right, and end up with our WML, right, what we actually, which we call the W under the maximum likelihood assumption, well, if we ignore the terms that don't depend on W, we see that we end up with an optimization that looks somewhat like this, right? So we're taking the derivative of minus beta over 2 summation n is equals to 1 up to n of yxn comma w minus tn squared. So we're taking the derivative with respect to w of this term, but this term is starting to look like something we already know, right? Something we saw in the second lecture actually. So we're finding the maximum likelihood of this. So finding the maximum likelihood, like maximizing the likelihood of this, right, should give us, like if we have beta in here, like we can actually take it out because beta is a constant, so it does not actually matter what our beta is. So if we actually expand this further, so our maximum is not going to change depending on the value of beta. So we can actually take out beta and we'll have something like this, minus 1 over 2. We just removed beta from here. Summation n is equals to 1 up to n y xn comma w minus tn squared. So we're trying to find the max of this, right? Which is the same as minimizing 1 over 2 summation n is equals to 1 up to n of yxn comma w minus tn squared. And minimizing this is something that we know that we did before. We talked about this equation over here, like here, which we called, if you remember, the sum of squared errors. Not the sum of squared errors, but the mean squared error rather, because we're actually, taking the average here. Sorry about that. So we were saying that this is our sum of squared errors, where this becomes the mean squared error, of course, if we divide by n. But as is, if we are trying to minimize this term, it's the same as, of course, finding the maximum likelihood of, like, this term over here. So this is something we're familiar with, and now we're getting an idea of where it came from. Like we talked about it in the second lecture, but we hadn't explained why we are computing this term in this manner. So there should be a bracket here. Okay. So that resolved that problem. Let me go on to a new page. Okay. And another thing that, of course, we can do, like we have found the derivative here, like when we're doing the maximum likelihood estimation, when we take the derivative of this term with respect to W, right, then we end up with this equation we see here, which is essentially expressing our error computation. And now we can do the same thing with respect to beta. So I'm not actually going to go through the whole computation here because this is something we already did in the previous lectures. So I'm just going to show what the output is. So ultimately we end up with 1 over beta ml, maximum likelihood here, being equal to 1 over n, the summation from n is equals to 1 up to n of y xn comma wml, where wml, how do we find it? By either minimizing this or maximizing this term. That's how we find it, which we do by taking the derivative of all this with respect to w. So this is just something that you should be familiar with from the previous lecture, because we had talked about how to find the maximum likelihood estimation for the maximum likelihood estimate for the Gaussian, and we're just doing the same thing, just the variables are different here, that's all. So where were we? So yeah, that's minus Tn squared, right? So the idea is that first we find WML, right? And then we find what beta ML is. So once we know what WML and beta ML are, then we can actually resolve for our unknown parameters in this Gaussian distribution. That's the idea behind this. So instead of just a normal point estimate like we had before, we now have a probability distribution over t, right? Where we say that the probability of t given x, comma, our weights w, then we have beta ml. This is just a normal distribution, right, over t given by our mean. So the mean of this distribution is actually given by this predictor function yx comma wml, and the variance is just the inverse of the precision, right? This is the idea. So we can express this t, the value for t, after we've actually found what wml is and what bml is. We can actually express this whole probability by using our Gaussian distribution as follows. So what we end up with is not just a simple point estimate, but, well, when we really think about it, let me just draw some simple example here of some points we might have. So these are just our data points, and let's say we plot our nice looking curve, okay, not perfect but something like that, and then someone asks us like what is the value of x0, right? So this is the question that we're asked. So the answer to that would be, okay, this is our x, this is our t. Well, we come over here. Let me just have a couple more points here for illustration. Okay, so we come over here, this is our point x0, right? And this is the corresponding value, which is represented by y x0 comma w, right? Where w is wml. And essentially what we end up having, right, is let me use another different color, maybe. Okay, no, we already used this one. Okay, let's use pink. So we end up with this, Gaussian distribution, where this part here is showing the, let me draw it again to, yeah, more like that. So this becomes our distribution, which is represented by probability of t given x0, w, beta, right? So that means the output here becomes a distribution, right, over t, not just a point estimate. So now we can actually express kind of like our uncertainty, right, in a sense. But if you think about it, it's still not a full Bayesian treatment, right? And we're actually going to come to that a bit later, but let's actually take a step towards a more Bayesian approach, right? So we are just doing maximum likelihood estimate here, right? So there's nothing new here. But, okay. First, when we're taking a step towards a more Bayesian approach, the first thing we need to introduce is a prior. This is something that we discussed in the previous lectures. So our prior here, P, W given alpha. So we're gonna use a prior over W, which is our weights, right? And we're going to just parameterize it by alpha, right? And say that it's actually following a normal distribution, right, over W with mean 0, and sigma squared, which is alpha minus 1 times the identity matrix here, right? That's the idea. So this is actually taking a step towards the multivariate Gaussian. So this is the Gaussian that we're using as our prior. So we're going towards a more Bayesian approach, and this is, we can write this as alpha over 2 pi multiplied by m plus 1 over 2 times the exponent of minus alpha over 2 w transpose w, right? And this is of course something that we can dive deep into now, but I thought it better to actually go into it in a future lecture when we actually start talking about the multivariate Gaussian, right, to understand it better. Actually, I had indicated it at some point in the previous lecture, the formula for the multivariate Gaussian, but for this you can just take it as is for now. But don't worry, we're going to discuss it further later on. So we call like alpha, this is our precision, right, for the distribution, where the precision is 1 over the variance, if you remember. And we say m plus 1, this is total number of elements in W, right? So this is total number of elements in the vector W, right, of mth polynomial. So this comes back to, so this is actually coming back to our model selection type of things we discussed before. Again, not something that we need to concern with ourselves with now. It's more like hinting towards what we're going to be talking about in future lectures. Okay, so we now know what this is representing. We have our prior, right, which is represented by this term, right? So what we can do is say, well, we can take we want to find probability of W given x, comma t, comma alpha, comma beta, right? So some of those things here, of course, are vectors and stuff like that. I'm just skipping this notation for now. I think it should be just kind of clear what it is anyway at this point. And we say this is actually proportional to the probability of our likelihood, which is t, which we said is given by x, comma w and beta, right? So this is our likelihood, x, w, beta. That's what our likelihood is. So we take our likelihood and we multiply it by our prior. So this is our likelihood, this is our prior, and this is our posterior, right? This is something that we had, of course, also discussed before. So again, nothing new here, right? So these terms like alpha and stuff like beta, we call them hyperparameters. We're gonna go into what that means later on. But the thing is that we can actually determine the most probable value of W given the data. So we're trying to find the probability of W given the data, right? By maximizing the posterior distribution. So what we want to do now is, before we're maximizing the likelihood, now we want to maximize the posterior. And where this was called maximum likelihood estimation, right, we call this maximum posterior, or rather MAP, right? So you might have seen this before somewhere. This is essentially what it is. So we are trying to maximize the posterior, and by combining some of the equations we've already encountered. So the first one is, let's call, so you can do this yourself as an exercise. This is equation number 1, right? And the other equation that we encountered was for the, so this is equation number 1 for the, what you call it, for the log of the likelihood. And the second one is the one we see here, right? So essentially, what we want to do is take the log likelihood of this whole term, right? The log of this term, and maximizing it. So by taking the log of the likelihood multiplied by the prior and maximizing that, we end up maximizing the posterior. That's the idea. Maximizing this term is the same as maximizing the product of these two terms, right? That's the idea behind this. So you can do it as an exercise for yourself because you already know what this is. You know what this is. You can just, multiply the two, take the log, and because this is quite similar and it's pretty straightforward to what we already did before, I'm just going to skip through that. But essentially, what we end up with is we end up taking the minimum. So maximizing this term is the same as minimizing beta over 2, right? Summation from n is equals to 1 up to n of y xn comma w minus tn squared, right, plus alpha over 2 w transpose w. Okay, so how else can we write this term? We can take beta out, right, and we end up minimizing. So if we take beta out, it's like beta times the minimum of 1 over 2 summation n is equals to 1 up to n of y xn comma w minus tn squared plus alpha over beta, right? This is one way that we can represent this. So we can say alpha over 2 beta, I guess, since we have a 2 here, but we can also take out beta over 2, I suppose, but no, it's fine. W transpose W. So here I'm just roughly writing what we are doing here. But the idea is that since this is a minimization operation, whether I multiply it by a constant, it doesn't really matter. And here, this term, we can more generally just represent it as by this lambda, which is equal to alpha over beta, in generally speaking, right? So we can take this term and then just say, okay, alpha over beta is representing lambda, which we call our regularization. Regularization parameter. So this is something you might have encountered. So if you had taken some introductory courses to machine learning or something, you might have encountered what regularization is and so forth and so forth. So this is something that we can tune by using this term, by using this lambda here, which is alpha over beta, right? So this is a hyperparameter as well, so which controls regularization. So we're going to discuss what those things are, of course, in future lectures, but this is just to show you like how maximizing the posterior, right, which is essentially maximizing the product of the likelihood and the prior, ends up in us minimizing this term, which we might or might not be familiar with from, basic machine learning. But in any case, this should give you an idea of what it is. So, okay, so we have our regularization parameter. So we included this prior, right? And the thing is that we are still making a point estimate for W, right? Of course, for T, we already say that when we're doing our whole, we now have a predictive probability over this whole data set, where its probability of T is given the value of W and beta and so on. But the thing is that we're still making a point estimate for W, so we are not actually given this a full Bayesian treatment. So the question is, how would we go about doing that, right? So this is something, again, that is a bit involved, and we will actually go through the proofs and the equations and stuff in future lectures. But just to give you an idea, is that we start at this whole point by saying we're given some data X, right, and some target T, right, and we're given test point, say X, and from this test point we want to predict the corresponding value T. Now I'm just distinguishing the vector forms and the scalar forms of this. So we say that we want to evaluate the following predictive distribution. So the probability of T given our test point X and our entire data set X and T. This is essentially what we want to find. Well, this is equivalent to the integral of P T given X, W times the probability of W given X, T. Right. So, okay. Let me try to use a different form to make things much more clearer, because it is okay. So I'm just going to make things bold, I guess, for this W, but it's also a vector actually, so it's still fine. Probability of W, given X, T dW, right? So this is essentially what we have. So never mind the notation. So this is essentially a vector. This is another vector, right? So this is essentially what, and this is our test point t and our like test point x and the corresponding value of that, which is t. So this is what we have, right? But we already said how did we actually reach this point where we say this probability of the target variable given some test point in the data is this? Well, we're just using the product rule and the summation rule, right, of a probability as we did before. So if you remember from before, when we say we're given probability of A, well, this is the summation of a y of probability of A, let's say summation of a B, or probability A comma B, right? And we say probability of A given B is equals to probability of A comma B is equals to probability of A given B times the probability of B. So that's the same idea here. We're looking at probability of T, right? Given X and all this data, well, we can just take it as the probability of, since we're already given, right, what this, well, X is. So we ignore that, but we say probability of T given X, which is already given, comma W, right? So we're marginalizing over W. So we take this integral. That's the idea behind this equation that you see here. Okay, so we've resolved for this. And we said that the probability of T given X, comma W, right? This is given by the normal distribution, right, of T given Y, X comma W, beta minus 1, right? This is what it's given by. And the probability of W given X comma T, the one we see here. Well, how do we find this? Well, we can do it by, we just need to normalize this term over here, normalizing this posterior. So we divide this by the integral of all of this. So this should be something you're like familiar with from the previous lecture as well. Right. So this is essentially a posterior distribution over parameters, right? So right now, of course, there is an analytical solution to how we actually solve for this. I'm not actually going to go through this in this lecture because it's already been too long, and this is something we're going to cover in more depth in future lectures, but this was just to give you an idea or a feeling of what we are moving towards when we start talking about a Bayesian treatment for all of these things. So hopefully this is something useful to you, but I'm going to end this lecture here, and hopefully it just gave you a guide or a feeling of what we mean by we are trying to move towards the Bayesian treatment for polynomial curve fitting, as in one example. We're going to be doing this over and over again, and we're going to go in more detail than we have in this lecture. This lecture was more of a feels lecture. But yeah, I hope this has been useful in that sense. So I'm going to end this lecture here. Thank you.